All right, now we're going to move on to Kepler's laws of orbits. So first, we have Kepler's first law, which describes the shape of possible orbits. So we have all planets orbit in an elliptical path, with the sun as one of the focus points. So an ellipse has two focus points that are symmetric about the center. This just says that planets orbit with the sun at one of the two focus points. And if the orbit isn't closed, we do get more options. They just have to be conic sections, and we'll go into that when we look at the unbound cases in the first problem here. Second law says that if we draw a line connecting the central star to the planet, that line is going to sweep out area at a constant rate. This is also known as the equal areas and equal times rule, which says that if the times of two segments are equal, that means that the areas swept out in those segments are also equal. So you can see as a consequence of this, it means that a planet's speed is going to change as it orbits. Because if you're somewhere that's really far away, like this, for example, notice that you have the benefit of distance, which allows you to sweep out a lot of area in a short amount of time just due to your distance, which means that when you're looking at the other side of the planet, you must have to speed up in order to account for that decrease in radius. So what this says is that as radius increases, v actually decreases proportionally. And this is a result of L being a constant, or angular momentum being constant. And we'll show that it's conserved and why that's so important. And the third law, in equation form, it just says the square of the orbital period is equal to a constant times the cube of the square of the semi-major axis, which is the big radius of an ellipse, or it is just r if you're in a circle. But if we prefer to look at it in comparing two objects orbiting the same star, we'll just divide the two and get that the squares of the periods have to equal the same ratio of the cubes of the semi-major axes. So now we'll draw some possible orbit shapes. So first, let's suppose the total energy of the comet is negative. So we have this comet right here. It's going to orbit the sun. We want to figure out what kinds of orbits we can have. So we said before that in this first case, the energy is negative. And in the escape velocity section, we said that that means that your orbit is bound, meaning you cannot escape. So we have a bound orbit. And from Kepler's first law, we know that the only types of bound orbits that are allowed would be elliptical orbits, or the special case called a degenerate ellipse, which we just call a circle. So I do have the shapes kind of pre-drawn in here because freehanding it would be a bit problematic for me. So there are some possible shapes. So notice that we can get a circle, or you can get some sort of an ellipse. Basically, all of them are going to be ellipses, unless if you have the perfect conditions to make a circle. Total energy of the comet is 0. So we said this is the escape condition. So this is where you escape and have 0 kinetic energy at infinity. And at this cutoff point, we get our first other conic section where we get a parabola. And it will just look like our standard parabola. So it almost looks like it could close upon itself and become an ellipse, but it's not going to. So So it's just going to come in, and it's not going to close on itself. It's just going to keep going. And if you have positive total energy, you escape, but with kinetic energy as well. So this is an even more severe escape. So this also escapes. And this orbit is a hyperbola. And it can be tricky to see the qualitative difference between the two. And in reality, it isn't that big of a deal. Just like a circle's a special case of a parabola, a hyperbola is a special case of the parabola. So it's just going to look even more pronounced as an escape. Sort of like that. And there's our possible orbits. So they are actually just the conic sections. It's just if you're bound, it's a circle or an ellipse, and if you escape, it's a hyperbola or a parabola. Okay, onto the second law. We'll prove this one. Provide a proof of the second law. Well, Kepler's laws for elliptical orbits. We're just trying to prove that area is swept out at a constant rate. So let's find an expression for the area of this wedge and show that it increases at a constant rate. So we'll start with some labeling. So we'll call this small angle d theta. So assume we're zoomed way in. So this angle will be d theta. We cannot assume it's a circle. If it's a circle, it's very easy to prove. But that's d theta. We'll call this distance r at this point. And we want to find the area of this wedge. So to do that, we're also going to need to estimate the length of this segment right here. And notice that that is just a little arc length. So that's going to be the same as r times d theta, because it's approximately circular at this time. So that means that our area, either using the area of a sector formula, or we can just approximate it as the area of this little triangle. Because if we're moving very, very, very small in time, it is going to look like a triangle. It's just going to be 1/2 times the base times the height. The base of the triangle we said was r, and the height we said was r d theta, which means that the area of our little wedge is 1/2 times r squared times d theta. So then just to get it into a rate, and we should actually call this dA, which is a very small area. dA dt is just going to be dividing that side by dt. And we'll associate the dt with the d theta so we can do some more substitutions over here. So d theta dt is omega. So we can go on in and plug that over. So dA dt is equal to 1/2 r squared times omega. And now for the only hand wavy step of the proof, we're actually going to multiply top and bottom of this expression by the mass of the orbiting planet. And then we're going to associate one of the m's over with the 2 on the bottom. And now we get mr squared times omega. And due to this planet orbiting at a distance of r away, it is just a point mass. So mr squared is actually just the moment of inertia of the point mass times omega. And I times omega is just the angular momentum of the system. So we're seeing that dA dt is equal to the angular momentum divided by 2m, which we're hoping to say is constant. So if we can prove that L is a constant for this planet, we can show that Kepler's second law is true. So to do that, recall that the net torque on a particle is equal to the rate of change of its angular momentum. So if we have no net torque, we have no angular momentum change. And for this, I think it's most straightforward just to look at the fact that if we have our planet and we have our central star, just due to how gravity works, gravity is always going to act on the line connecting the two planets. So that's going to be F. And then R is also going to be along that line. And if we want to think about the cross product definition for torque, where torque is equal to R cross F, well, that's going to be equal to 0 for this case, because R cross F can also be thought of as the area of the parallelogram you can make with R and F. Well, if this is R and this is F, well, this has 0 area. So the cross product of two parallel vectors is just 0, right? You can't generate a torque by pushing along the pivot point. So that means that dl dt is equal to 0, so L is equal to a constant. And again, it's because the force is parallel to the r vector. So there's no torque caused by gravity, and that's equal to a constant. And that ends the proof. Then just for a basic example here, during the month of December, the Earth sweeps out an area of A during its orbit. What area does the Earth sweep out during the months of July and August together, we'll say? So we know that by Kepler, dA dt is a constant. So the area is swept out at a constant rate. So in December, which is 31 days, we're sweeping out an area of A. Well, that means that July plus August, well, they're both 31 days as well. So it's just twice as much time. So we're sweeping out twice as much area. And now for a classic angular momentum problem with the second law is applying it to elliptical orbits. So first, we have this planet of mass little m. It's orbiting a star of mass big M. At apogee, which is the farthest point, it's 10r away from the star. And then at perigee, it's at a distance of 2r. And we're going to be asked to compare these speeds. So first, explain why angular momentum is conserved. Well, as we looked at before in our proof of the second law, we have a planet being attracted to a star, but due to the law of universal gravitation, the line of action of the force is exactly along the line connecting the two particles. So my force of gravity is going to point directly on the connecting line, and the connecting line is also, by definition, what our torque r vector is going to be. So torque, which is equal to r cross f, is equal to 0, because you can't form a parallelogram out of these two vectors. It makes no area. Because cross product is about perpendicularity, and if they're parallel, it's 0. Just like the dot product of perpendicular vectors is 0, the cross product of parallel vectors is 0. So since the torque is equal to 0, angular momentum is conserved about the center of the star. Then, using conservation of L, explain why the planet must speed up as it reaches perigee. So, because angular momentum is constant, we know that L at apogee is equal to L at perigee. And also, since we have a point mass that's orbiting, we know that we can use orbital angular momentum. So we can say that mVA RA has to be equal to mVP RP. So we get this form of the second law, which says that the product of V and R has to remain constant. So anytime you have two things multiplying to a constant, that means they're inversely proportional. So, why must it speed up as it reaches perigee? Well, as we reach perigee, we get closer. So if R is decreasing, that means V must increase. So as R decreases, we must get V increases because R times V is a constant. And now let's actually solve for it. So we did say that just using angular momentum conservation, we showed that VA times RA equals VP times RP, which means that solving for VP, we just get VP equal to VA times RA divided by RP. And now let's plug in some values here. So R at apogee is 10R, and it's 2R at perigee. So we get VA times 10R divided by 2R, which just gives us 5 times V at apogee. So if we're getting 5 times closer, we must be moving 5 times as fast, which is how you could have done that without using the equation. Two planets are in elliptical orbit around the same central star. Planet X orbits at 4 AU and takes 2 years to complete one revolution. Anytime you're talking about period and orbital distance and revolution time, it's probably a Kepler's third law problem. So, explain how Kepler's third law proves that planets orbiting at further distances take longer to complete a revolution. Well, Kepler's third law says that t squared is proportional to average orbital distance cubed, which is also known as the semi-major axis. So, why does it take longer? Well, since t squared is proportional to a cubed, as a increases, t increases as well. That's all it is to it. Because they're proportional. So increasing one increases the other. Doesn't matter that one's squared and one's cubed. Increasing one is still going to increase the other. If planet Y takes 6 years to complete a revolution, solve for its average orbital distance. So we should probably use the ratio form of Kepler's third law for this. So we're given the distance and period for planet X, and we're given the time for planet Y. So we'll just use the ratio form of the second law, which says, the third law, which says that the ratio of the squares of the periods is equal to the ratio of the cubes of the semi-major axes, or average orbital distance. So, plugging in, we're given that planet X took 2 years, planet Y took 6 years, and we're given the average orbital distance of planet X was 4 AUs. So then simplifying, we get 1/9 is equal to 64 divided by AY, quantity cubed. So we get AY is just going to be the cube root of 64 times 9, which is going to be a not very nice number. It's going to be 8.3 AUs, roughly. And that's our answer. So we just set up a proportion and solved. And then last, suppose you're given a list of orbital distances and periods for a set of planets in our system. Explain how you can use a best fit line to estimate the mass of the sun. So we're given the average distance, which is A, for semi-major axis, and the orbital period, T. And we want the mass of the sun. So with any of these lab questions with a best fit line, it's always important to first write down the governing equation without figuring out linearizing or anything like that first. We're just going to write down an equation. So what relates these two pieces of data we have? So we have A and T. So that's the third law. And in equation form, we have that Kepler's third law says that T squared is equal to 4 pi squared over gm times A cubed, as long as the m is the same for all the bodies. We're allowed to say this equation applies for everything, and it is because all of these are planets orbiting our sun. So now to figure out what to graph, there are multiple options. I would start just by getting everything that is a variable over to one side, because we want to set up a rise over run situation. So A and T are our variables. So I'm just going to divide by A cubed to get all the variables on one side. So I get T squared divided by A cubed is equal to rise over run, which is equal to a slope, which is equal to 4 pi squared over gm. Because again, if you get all your variables on one side, that means that there's a constant on the other side. So this means that the ratio of T squared and A cubed is constant, meaning it makes a straight line. So this is how we should do every best fit line question, is to just set up our expression that gets us a constant when we divide everything over. So that means we're graphing T squared versus A cubed, or anything like that. So notice I could have done any sort of exponent I wanted to this expression and it'll work out. You just get a different slope. So you could have graphed A cubed versus T squared. You could have graphed T versus A to the 3 halves. You could have graphed A versus T to the 2/3. Any of those works. And then once graphing these, we said that the slope is going to be equal to 4 pi squared divided by g times the mass of the sun. And if we're solving for the mass of the sun, you can see you're just going to end up swapping the positions of the slope and m. So 4 pi squared divided by g times slope. You will get a different slope expression, again, if you graphed something different. It just has to be something that can be equivalent to t squared versus a cubed. As long as you're dividing the variables, getting them all on one side, you can square root, do whatever you want. You just have to be able to manipulate the slope expression to solve.